this should be a pretty straightforward course. It's going to be starting at chapter 6, and it's going to go through the end of the text. Let me tell you one other thing, too. I'll give you problems besides Dr. Wentworth's book problems, and I know there's solutions manuals. I give you the solutions anyway. And the reason I do that is because I think some of his problems that are very base level, they don't really challenge you, and I'll try to create problems that will be more challenging, where you'll really have to think your way through it. Now, besides that, I think we can jump right into this and start. This is going to be chapter 6. How many have Riggs for EMEG 1? How many have Wentworth? All right, so more people have Wentworth. Wentworth goes right through chapter 6, doesn't he? I mean, right up to chapter 6. He's done with the last part of chapter 5. Isn't that right? You all have him, right? Yeah. You remember? Yeah. And then, did Riggs finish chapter 5 or not? Did he do wave equation? Did he put the Maxwell's equations up?
Yes.
All right. That's our starting point. We're going to start with that, and let me just say I appreciate your recording this. And if I need a mic or anything, let me know if you can't hear me.
Okay.
What I'm putting down are the most fundamental form of Maxwell's equation, and we don't use English units, we use SI or MKS units. So the two equations are curl of H is equal to really J plus the partial of D with respect to T. And this one is called Ampere's law. And the second one is curl of E equals minus dB dt. Now, do you remember what this one's called? You had part of this in EMEG 1. Anybody? Guy that has my same first name. Michael Faraday's law of induction. This is Faraday's law of induction. There's a book, it's a two-part series, it's called, it's Maxwell's Treatise on really electromagnetics. It's interesting because this is an old Scottish scientist, a physicist that came up with this. Now, just to recap, H is going to be in amps per meter is a magnetic field. B is a magnetic field intensity. It's in Webers per meter squared. You don't need to write this down. I'm going to go through this slide. I just mentioned J is the actual current density. When I say current density, it means real current, like electrons moving in swarms through a material. That's J. dD dt is called the, do you remember the name for this, anyone? Yeah, Wentworth, you probably do. Displacement current. Do you remember displacement current? Displacement current has no real charged particles moving. For instance, if you have two plates of a capacitor and there's a vacuum between them, if I put an AC voltage on those capacitor plates, there's a current that flows, right? There's no charge moving from one plate to another. Charge is being induced to move off of the plate by what? Mutual repulsion of charges, right? Well, that's what's called, or attraction, either one. That's the current that is caused by the displacement current density, and that's this. Now, the E field is in volts per meter, and that's something, it's measurable, very easily measurable. You can measure an electric field by developing, if you have an electric field that's incident on an antenna, then the voltage across that will be the integral of the E field over the length of that antenna, and we'll get to that more. It's easily measurable. The B field is measurable too. Now the relationship between all these things, the linkage is done by constants in terms, and we use this. We say J, or the conductivity, is equal to sigma E. Sigma is called the conductivity. How many remember that? Conductivity is something you got in EMEG 1. You have to know this. It's conductivity. Then D is equal to epsilon times E. Here, epsilon is epsilon relative times epsilon naught, and epsilon naught is really 1 over 36 pi times 10 to the minus 9 farads per meter, or it's 8.854, this is an approximation, times 10 to the minus 12 farads per meter. We use this a lot because it makes calculations easy by cancellation. And epsilon relative is something that just gives us an idea of how much more energy that material can store than free space. Remember when you added a dielectric, when you had electrostatics, a dielectric with a higher permittivity for a given voltage, you could store more energy. Do you all remember this class? This is something, and there's other reasons. Epsilon relative, the epsilon of permittivity also allows you to have a larger field strength. These are material characteristics. Then there is the relationship between B and H, right? And here, mu is mu relative times mu naught, and mu naught is 4 pi times 10 to the minus 7 henries per meter. And again, mu relative and epsilon relative vary from about 1 all the way up to maybe 10 to 20,000. So they have they have orders of magnitudes of values difference. For instance, what do you think the permeability is of this magic marker, or this marking pen? Permeability. Just throw it out. It's 1, right? It's just like air, right? There's nothing metal that suggests it could have a magnetic quality to it. You follow me? But if you take a bar of iron, the permeability could be 1,000, or in stainless steel, maybe 10,000 in some cases. So permeability is something that's related to magnetics, and permeability has to do with the ability of the material to store more magnetic energy than the actual free space could. Remember, that's what these things really index. Both mu relative and epsilon relative, these two quantities, tell you how much better than free space they are at storing energy. That's my take on it. There's other, you can look at other definitions, but that's the easiest one. And these are the things that would couple all these equations, all right? Now, something to be said, you have to know these two equations. All right, and you also have to know how to derive what I'm about to do. It's called a Helmholtz or wave equation. Now, we're going to do one other thing too. I do this as an aside whenever I have this class or EMAG 1. You've had phasers, right? You've used phasers extensively either in your circuits course and somewhat in EMAG. Back in the day when you had a voltage, if I say I have a voltage of 10 at an angle of 30 degrees volts, that's something you can liken to a source, right? What's not stated there is the frequency. Do you follow me? This is a phasor identity. It completely extinguishes the e to the j omega t term. Now, if I have this, I can also write it as 10 times e to the j 30 degrees. You all agree with that? That's called exponential notation. By the way, you know, if you guys can see what I'm doing up back there, it's fine. But if you want to move out front, it'd probably be better for you. But, you know, do what you want. Are you with me on this one? Now, these don't show the time domain form. This is really a phasor. How many have had Dr. Gross? You know, he would yell at me if I didn't put a tilde on that. But I'm just going to tell you, anytime you see a j, e to the j something, it's in the phasor domain. I don't need to indicate that, so I might be a little sloppy. Now, if I want the time domain form of this, what I do is take the real part of the phasor domain form times e to the j omega t. Now, sometimes people don't realize this is what they do, but this is the way you go back to the time domain. We suppress e to the j omega t when we're in the phasor domain, right? Now we multiply by e to the j omega t, but we have to take the real part, or the projection on the real axis. What it amounts to is this. It's the real part. Technically, they usually put in curly brackets here, of this phasor, which is 10 times e to the j 30 degrees times e to the j omega t. Right? Now, if you have e to the a and e to the b, and you multiply them, that's really e to the a plus b. You add exponents. So what this is really the real part of 10 times e to the j omega t plus 30 degrees. And that's the voltage, V of t. I'm going to go a step further. After that, I can say the real part of any of this can be found very easily. By the way, does everybody understand when I say real part of something, what it means? For instance, if I say that A is equal to 10 plus J5, what's the real part of A, just by inspection? 10, right? It's that easy. It's the part that isn't imaginary. And if I had something where I had, instead of this, if I had 10 at an angle of 30 degrees, what would the real parts be of 10 at an angle of 30 degrees? Let me help you with this one. First, actually plot it so you get a visual picture. 10 at an angle of 30 degrees, I put it in exponential form. If this is the real axis, and this is the imaginary axis, then what I have, or j-axis here, I have a vector of length 10, right? And it's at an angle of 30 degrees, correct? Now the real part would be the projection of this vector here. And that would be the cosine of the angle times 10. Do you all see that, class? Give me a show of hands here. I want to make sure you're quiet. It's after lunch. I don't mind the sleepiness. I'm like that too. So when I take the real part of this, what I'm going to do is take the cosine of this angle times 10. Follow me? So that means V of t here would be equal to 10 times the cosine of omega t plus 30 degrees. That's sort of a review of going from phasor to time. And by the way, if we wanted to go from time to phasor, this is the easy one. They're both easy. You take the simple magnitude, it has to be in a cosine format, it has to be like cosine omega t plus a phase angle, or plus information. You always take the magnitude, and you put it at the angle, or anything next to omega t. Follow me? That's the way you always do this stuff. All right, so that's phasors, a review in a nutshell, because some people will not appreciate this, and then they get themselves into trouble with the course. So, going back to this, now what I'm going to do is, oh, one other thing. When you have a derivative in the phasor domain, d dt translates as j omega. And let me just give you an example of this. Do you remember current relationships with inductors? It was V in an inductor is equal to L times di dt. Do y'all remember that, class? L di dt is the voltage across an inductor. Well, in the phasor domain, that's what voltage across an inductor is J omega L times the current in the inductor, or really the impedance of an inductor is simply V over I, or J omega L. Most of you remember that, right? In circuits. And you'll have to know this well. So anytime there's a time derivative, it just brings out J omega. I'm going to do what I'm going to do in the phasor domain. And the reason is because it's less work. I can do it in the time domain. Maybe it isn't truly less work, but for me, I like doing it this way. So I'm going to take all these quantities, I'm going to make them phasor, all right? First. When I do that, I have curl of H is equal to J plus, then it would be J omega times D, and I would have curl of E here equal to minus J omega times B. Does everybody agree with that? Here, I've just replaced the derivative with a J omega. Follow me? Now, after that, the next thing I do is I'm going to substitute in, because I want these two equations to, I'm going to combine them in a second, but I want them to be a function of only one variable. Follow me? So first I'm going to turn everything into E's and H's and just put the coupling coefficients. So the first equation here, let me do it right here. Just see this. I take the first equation, curl of H, or I'm sorry, I'll take the second equation first. I'll take curl of E, and I'll say it's equal to minus J omega, and now I'll replace mu, I'll replace B with mu H, times mu times H. So I have that equation, and then I have curl of H here equal to J, which is sigma E, right, plus J omega epsilon E. And you can see what I've done is substitute. I've substituted in for J sigma E, for D epsilon E, for B mu H. All right? Y'all recognize this, guys? Does this look vaguely familiar? Now I need one equation with one unknown, and this is just the general trick. Whenever you have two equations with two unknowns and you need one equation with one unknown, and there isn't an obvious exchange, there's a couple ways to do this. Really, the easiest way for this is take another curl of that. So let's take another curl of that, and I get what? Curl of E is equal to minus j omega mu times curl of h. Are you with me? What does that buy me? Well, look right above what the curl of h is. It's all in terms of e on the other side, is it? Can you all see that? So I can say that now my curl of e is equal to minus j omega mu times curl of h, and curl of h is going to be sigma plus j omega epsilon times e. Something I'm going to say, I factored out the e from both of these, so I'm left with sigma plus j omega epsilon here, and then I have the j omega mu from above here, and I have a minus sign, and then I have this curl of e. Now, this is something you probably don't remember, maybe somebody does. Curl of e is a vector identity. You did not have vector calculus, did you? You had just standard scalar calculus. Did you have Stokes' theorem? You did have Stokes and Green's theorem? Great. You probably remember this. That there's a vector identity if you have curl of e, that's equal to the gradient of the divergence of e minus del squared of e. Now remember, e is a vector term. E has generally three components, x, y, and z if we're in Cartesian, right? So now I have this. Can you all see this okay? All right, now, here's where it gets interesting. We want to get a solution to this in a reasonable way for a reasonable problem. So what we do is this. We're going to assume that the electric field that's caused by some charge phenomena, some acceleration of charge, it's going to launch away, and we're not going to be real close to the source. We're going to be a long way away. And one thing you know about waves, the further away you get from the source of the wave, think about just dropping a stone in a puddle. As you get further and further, you basically get a circle where contours of equal amplitude, or really the crest of the wave, and it's going to expand radially, right? What happens is the curvature, the radius of that thing gets bigger and bigger. Well, as it gets bigger and bigger, pretty soon, if the pebble goes here, instead of looking like that, it's getting bigger and bigger, and then finally in the limit, that starts looking like something where for a range of values of interest to me, it looks like a constant value versus, it doesn't vary in any direction but one, radially outward. You follow me? And it's called a plane wave. It means the wavefront is planar at a great distance. So this is what we're talking about. Now when we have a plane wave, let me show you. Then when we come to this, there's a couple things we can do. First, we can say it's charge-free, so mark that down. We assume this. Assume charge-free. Now, what does charge-free mean? Well, do you remember what Gauss's law is, anybody? The point form of Gauss's law? Anyone? You don't have to be shy. Anybody? No? Gauss's law is an important law. It was divergence of B equals rho V. Do you remember? And then there was the integral form of Gauss's law, was the integral of B dot ds around a closed surface was equal to the charge enclosed in that surface. That's the integral form, that's the point form, or the differential form. Gauss's law is so important. I mean, it's one of the fundamental things you have to kind of really appreciate. Well, D is related to E, right? D is epsilon E. So if you replace D with epsilon E, you get divergence of E is equal to rho V over epsilon, right? And if it's charge-free, it means rho V is 0. There is no free charge. There may be charge in the system, but the positive equals the negative and it's nullified, so it's charge neutral. So if there is no charge in the system, the divergence of B, or divergence of E, would be 0, and that would get rid of this term. So we're going to assume that. And for practical applications, when you're propagating through air, you can assume it's charge-free. When you're propagating through most materials, it's charge-free. The only time you really run into charged reasons is like ionized plasmas, and that's problems that you probably aren't going to encounter right away. But for the most part, it's charge-free. That means I'm left with this. I got minus del squared of E is equal to all this. So that's where I'm going to work next. And what I'm going to do is this. In general, a del squared operator, if I have just del squared of E, write this down for your edification. And we're in Cartesian coordinates, that means I have the second derivative with respect to x squared, plus the second derivative with respect to y squared, plus the second derivative with respect to z squared, all operating on ex ax plus ey ay plus ez az. Now, if you look at that, that means this ddx term has to operate on this, this, and this. This ddy term has to operate and this ddz, which means you have 9 terms. Follow me on this, class? That means there would be 9 vector terms here for that, which is a lot. You would have 3x, 3y, and 3z, all with partials in x, y, and z, which is a mess. So what we have to do is we can solve this but numerically, and if we go to spherical coordinates or cylindrical coordinates in some cases, we can get a very closed form solution. Do y'all remember the del squared operator, guys? You did it first with what? Voltage, right? That was a scalar. Then this is a vector del squared operator. It's called a Laplacian. So what we do is this. We assume that we're talking about a plane wave phenomena a long way from the source, and the E field is only oriented in one direction. Dr. Whitworth's book says the X. So there's going to be some E x ax. He assumes the E field has only vector component in the x direction, no y, no z. And the second thing is, he's going to assume that Ex is only a positional function of z. So this is only going to be a function of z. Got that, everyone? So now when he does that, now listen, it's only a function of z. That means derivatives of x and y are 0. Understand? The other thing it means is since it's in the x direction, we have no ey, ez. This is really what we have going on right here. That del squared operator is just going to be the second derivative of ex with respect to z squared. You follow me? So this del squared operator here becomes, I'm going to take the del squared and move it to the other side. So it's going to be the second derivative of ex with respect to z squared. And now it's got to have minus j omega mu times sigma plus j omega epsilon times e. Here's where we introduce a constant. Just make sure you watch this. You know, this can be real dry, but it's so important that you catch this. There's certain things that I'm doing that keep coming back to haunt you. This whole thing is equal to 0 because I took the minus del squared and I moved it to that side. Does everybody see what's going on here? Now, we're engineers, and one thing engineers are good at is trying to make things manageable, compact. The notation, you want something that's easy to work with. I don't want to have to keep writing this thing over and over again. So I'm going to introduce a new constant. What I do is this. I say that gamma squared is equal to j omega mu times sigma plus j omega epsilon, and gamma therefore is equal to the square root of j omega mu times sigma plus j omega epsilon, and that's equal to alpha plus j beta. Does anybody remember what gamma's called? You had it in your transmission lines. When you did transmission lines, you also had it in chapter 5. Anybody? Propagation. Propagation constant. Right, very good. So this is the propagation constant. Now, it's equal to alpha. Do you remember what alpha is, anyone? Attenuation. Coefficient. And beta, anyone? Say again? It's, phase constant, that's acceptable. Wave number, have you heard wave number? It's the wave number, it's phase constant. It's in radians per meter. This is phase constant or wave number. A lot of times instead of B or beta, it's K. It's represented by K, just so you know this in other classes that you have physics courses. Now, the attenuation coefficient here only has a non-zero value if sigma is non-zero, or, and you will see with complex permittivity, if the complex permittivity has a loss component. In other words, alpha means the energy is being dissipated. Now, if there's nothing to dissipate energy, there's obviously alpha 0. Because this has to do with the decay of the amplitude of waves. And I'll show you that in a second. So let me take it from here and move back here and get rid of all this. So I'm going to start right there, and now replace it with gamma squared. So I have second derivative of Ex with respect to Z squared. And then it's going to be minus gamma squared times Ex equals 0. So that's just a single equation with a single variable. All right? This is a very, I don't know if you remember this. You could solve this with Laplace transform, and just like in Z to T, if you want, it's an easy one to do with Laplace transforms. You know how you had everything was transformed from T to S? Do you remember that? Well, you could look at Z as T and do a Laplace transform solution of this. You can also do it, I mean, because what happens when you take Laplace transforms? That was the second derivative of something with respect to T with Laplace transforms. What do you get? S squared times E of X, right? And then it's minus S times the value of E in the time domain at T equals 0, and then minus the second derivative of the E field in the time domain at T equals 0. Well, anytime it's steady state, you get rid of those derivatives. This is just going to be S squared minus gamma squared times E Laplace equals 0, and then you could do a Laplace transform solution and you get two exponentials. I'm not going to go there, all right? I'm going to do it. The way that in Wentworth's book he does it, he simply says, we know the general form, that's a second order differential equation, right? And it's homogeneous, it's set equal to 0. Do you all remember how to solve that? Your characteristic solution would always be what? Ex in general has the form A times E to the lambda, remember eigenvalues, lambda z? You remember this? In other words, you just put in an exponential there. And you got a lambda. Now you're going to solve for what that lambda is. So you can see if you put this in there, what happens if I take two derivatives of Ex with respect to Z? Don't I get what? Lambda squared times just Ex? Isn't that right? Because you would get lambda squared, right? First derivative, you get lambda, second derivative lambda, you get a lambda squared, then you get the original, A times E to the lambda Z. So it's that. And therefore I can rewrite this equation as simply lambda squared times Ex minus gamma squared times Ex equals 0. Or I can factor out the Ex, and I have lambda squared minus gamma squared equals 0. And the solution is obviously, well, maybe it isn't so obvious. I can take Ex and factor it. Now I have lambda minus gamma, right? And I have lambda plus gamma equals 0. Isn't that right, class? Which means the solutions are lambda is equal to plus or minus gamma. I agree. And really, let me just say this, too. The general form of the solution to this equation, doesn't matter how you do it, you get Ex equal to some Ex0, e to the minus gamma z, and that's plus Ex0 minus e to the plus gamma z. Now, that is an electric field that has oriented in the x direction, don't forget that, but it's propagating in the z direction. This term is propagating in the plus z. The other term is propagating in the minus z. Are you with me? I'm going to take it to the time domain in 1 second. Is everybody with me on this? It seems warm in here. I don't know if it is to you. No? You don't feel warm? All right. Fits me. Well, this is a phasor quantity. Now, just listen to me. If I want the time domain quantity, the only thing I need to do is take this and multiply it by, if I want Ex in the time domain, function is z and t, I take the real part of the phasor domain quantity, Ex tilde, and then it's going to be multiplied times e to the j omega t. And what happens when you do that? You're going to get Ex0, right? Let me do one other thing. Ex here, tilde, is actually Ex0 times e to the minus alpha z times e to the minus j beta z plus Ex0 minus, this is Ex0 plus, times e to the alpha z e to the j beta z. What I've done here is I broke out gamma as alpha plus j beta, and I separated these terms. Follow me on this, class? But why did I do that? Because when I go ahead and take the real part of that and I multiply it by e to the j omega t, what I'm going to get is a couple of cosine. I was here one time when we had a Senate meeting. Somebody says, it's a bomb. I don't think I'm going to win that war. All right. Now, just take a look at this. When I multiply this by e to the j omega t and take the real part, really the imaginary part here is minus j beta z, right? And the imaginary part here is plus j beta z. When I multiply those by e to the j omega t, they become a single argument, and the real part means I would get this. I would get Ex0 plus e to the minus alpha z cosine of omega t minus beta z, and I would get Ex0 minus times e to the gamma z times cosine better than that, times cosine of omega t minus or plus beta z. And it's in the x direction. This would be Ex as a function of z and t. This is a wave moving this way, plus c. This is a wave moving this way, minus c. Oh, you with me, everyone? Probably at this point, it's good to show you phase velocity. So now I'm going to talk about phase velocity and wavelength. Now you've had this, and phase velocity is u phase. You've had this in EMAG 1, but I know it's worth reviewing. So what I'm going to do is phase velocity. I'm only going to take a look at the positive going term right here. And we're going to do something else. We're going to assume it's lossless to make our life easy. So here I have an equation, Ex of z comma t is equal to some Ex0 cosine of omega t minus beta z. So the way you get phase velocity is first you do basically a snapshot in time, you graph it versus z, then take another snapshot in time a little bit later. So if we take a look at this, and we take a look at Ex of z comma 0, so time is 0, it would look like this. If this was space right here. And this would be z. So this is at t equals 0. Take a look at this. I'll show you one other thing. And this is just the magnitude. This is z. This is the origin right there. You all get an idea of what's going on, right? Now, when t is 0, I have the cosine of minus beta z, don't I? You realize the cosine, do you know the difference between even and odd functions, class? And how many do? You do? You do? Well, an even function is something where you have f of x is equal to f of minus x. It means the argument sign has no bearing on the value. For instance, cosines like that. Graphically what it means is this. If you have any part of the function on this side, it is the same as on that side for the same value. This is minus x, and this is plus x. The functions have the exact same value. Got it? And the easiest way to think about this is you take the actual positive value from 0 on upward in the positive direction, fold it this way, just wrap it around, it'll lay right on top of that. If it does that, it's an even function. Do you follow me? They'd say take the paper and fold it together. If both curves overlay each other, it's an even function. An odd function is f of x is equal to minus f of minus x. And an odd function is like this, a straight line. If you take a look at this, at any value of x, and go to minus x, in order to have these two wrap around, I have to take this value and multiply it by a negative sign and bring it up here. And then it'll fold. You follow me? So that's the difference. Now, cosine's an even function. And when I make t 0, I really have cosine of just minus beta z. It's the same thing as cosine beta z, right? Follow me on this, class? So if you graph that, it would look like this, right? This distance here would be considered a wavelength. This would be the wavelength. Do you all agree with that? Wavelength is what? The distance over which the wave really has one cycle. The next point it's over which it repeats itself. Do you all see that, class? That's the wavelength for a cosine waveform. Well, what is it actually? Think about this. How far did we go? Well, when you think about this argument, beta z, right? Beta z is 0 here, isn't it? And when I get 2 pi, is it? Right here? So if I have beta times z, and z is the wavelength, that's how far out I am, is equal to 2 pi, or the wavelength is simply 2 pi over beta. This is important, that's wavelength, and that's the fundamental definition of wavelength. There's a lot of special definitions, like a wavelength is in free space, it's c over f and things like this, but this is the general definition for electromagnetic. Now the other thing is phase velocity. Well, if this is a t equals 0, let me see if this marker works. Not well. No strong there. Better. So suppose I plot e of x, z, and then some delta t, some small amount of time. Now it'll look like this. And what it looks like is the crest moved from here to here. You follow me? But one thing about this peak and this peak that they have in common, can you say? It has the same argument. The cosine of omega t minus beta z is the same value. It's 0 in that case. Do you all see that? So the way we get phase velocity is this. Let me erase this. We say we have omega t minus beta z equal to some constant c, right? And now we take a derivative with respect to time of everything. So the derivative of time of omega t is just going to be omega minus beta is a constant, dz dt is equal to 0. And what is dz dt? Well, that is a velocity, isn't it, class? In this case, it's a velocity of the phase, because it's the phase that's a constant. So if I take a look at this, it means phase velocity would be dz dt, and it would be equal to omega over beta. And that's the fundamental definition of phase velocity. Now we'll have special definitions, but this is the fundamental definition. Understand, everyone? I have to go through this in order to do what I want to do. So we went from basic Maxwell's equations down to the general solution in one-dimensional space, you might say, right? A wave oriented in X, moving in Z. And we end up also throwing in a few other quantities. We put them in the time domain, we get phase velocity, and we get wavelength. So now we're well on our way to getting to the heart of the matter. All right, so that's the E field from Maxwell's equation. Now we need the H field. So, when we talk about the H field, remember we had the equation curl of E equal minus J omega mu times H, right? That was something that I gave you. Do you remember that when we took the second law, Michael Faraday's law of induction, we substituted for B and put mu epsilon there, or mu H, pardon, mu H there, and then we went from time to phasor form. So this is what we ended up with. This is Faraday's law of induction. Now what we end up doing is this. We have E, right? So we have E. Let me do it this way. I'm going to just do for the positive traveling point. We're only going to take a wave in the positive direction. I'll tell you about the negative in a second. So we have some EX0 e to the minus gamma z, and it's in the AX direction. That's our E field, right? Now, what does the curl of E look like? Well, the curl of E, you can do it a couple ways. I like to determine it. AX, AY, AZ, DDX, DDY, DDZ, and then the values. This is EX. It has a form of EX. It's EX0, e to the minus gamma z. EY is 0, EZ is 0. Y'all remember determinants and how to do them, huh? You'll do a lot of these. So that's just a fundamental determinant. The way you get it is you basically take AX multiplied by DDY times that. That's 0, I don't care about that. Then you take AY times DDZ times this. So this is going to be AY times DDZ of the quantity EX0 times e to the minus gamma z. Right? And then you take AZ times DDX of 0, which is 0. And then you subtract from it, right, this term, which is ddy operating on this. Since this is not a function of y, it's 0 times AZ, and everything else is 0. That's your curl. How many remember doing curls? You're going to be doing a lot of these. Matter of fact, the one thing I'll say to you about engineering, electrical engineering especially, electrical and mechanical, is it is heavily reliant on mathematics, higher level math, and you have to have a very solid handle of that to do most of the work. Because there's not just something with small little formulas. These things are based on fundamentals of curls and divergences and things like that. So you have to understand all this stuff. Now when I take a derivative of that, I get what? I get AY. What's the derivative of this with respect to Z? Take one look. You're a chatty bunch, right? This is the quietest class I've ever had in my life. Never seen anything like this. It's what? This is the only thing that varies with Z. So a derivative of e to the minus gamma z would just bring out a minus gamma, wouldn't it? Sure. So this becomes a minus gamma, right, times EX0 e to the minus gamma z. Now that is the curl of E. So that's the curl of E. Where does it go? Right there. So I can say, if I take this equation and I assume that in for that, I get H, right, equals, and I'll put 1 over minus j omega mu. Here I'm taking the minus j omega mu and I'm dividing into the curl of E times the curl of E. Well, the curl of E is minus gamma times EX0 times e to the minus gamma z in the AY direction. You all see that, class? And what do you see happening? The minus signs cancel, for starters, right? And now I have this. Now, let me tell you one other thing. This will be some value hx0 e to the minus gamma z. It has to have the same, the actual same rate of change in z as the E field. The two are, they're married together. You can't separate them. Where an E field appears, so an H field appears if it's time invariant phenomena. And that's just the way it is. And this is normally how we express it. Now you'll notice one thing about this. This is H right here. I could say that H itself is defined as gamma over J omega mu times the E field but here we get into something interesting. You'll also notice that's equal to Hx, or Hy, pardon. Hy is, and the reason is this is now in the y direction. Hy0 times e to the minus gamma z. Just catch your breath. I know this is a little dry until it's applied, but just work with it. Y'all see this right here? Now, what do you notice happening here? Just look at this one. This is in the y direction too. I put that in. Well, if we get rid of that middle guy, that's equal to that, right? You see I can get rid of this exponential on both sides? Right? After that, I can get a ratio. I can get rid of AY too, might as well. Doesn't do anything for me. And now I can get a ratio of EX0 to HY0. Now the E field's in volts per meter, right? H field is in amps per meter. Volt over amps is ohm, right? It's ohms, which is a very, very important quantity. This is called this is the characteristic impedance. The symbol is eta, and this is the characteristic impedance. And that is simply gamma over J omega mu. Now I'm going to reduce this a little. Y'all see this right here? So what is gamma? From before, gamma was equal to what? Square root of J omega mu times sigma plus J omega epsilon. I mean the propagation constant. Wasn't it, class? I know it's been a while, but we did this early. Do y'all remember this, the propagation constant, how I developed it? Now, what happens when I do this? Y'all see I've got J omega mu here to the 1/2 power divided by J omega mu, right? So really what I have is this. I have the square root of hold it. You know what? I get this upside down. What I should have done is E over H would be J omega mu over sigma. My bad. Do you follow me? I had it reversed. This is, if I take EX and divide both sides by HY0, right? I get EX over HY and I have to flip that. So that's equal to J omega mu over square root of J omega mu times sigma plus J omega epsilon. In here, now I have J omega mu single power, J omega mu to the 1/2 power. Now I can rewrite this as square root of J omega mu over sigma plus J omega epsilon. And that is the intrinsic impedance. This is equal to eta. Or, characteristic, intrinsic impedance. Characteristic is what you use for waveguides. This is intrinsic impedance. What the word intrinsic implies, it's a property of the material at a point. If you look at characteristic impedance of a waveguide, it's something that has to do with bulk parameters, right? Overall. So, this is it. Now, this is an important, what I'm about to tell you is important. That's J omega mu over sigma plus J omega epsilon. So let's take a look at this for free space. Free space means a vacuum. So what is the value of eta? And this would be in a vacuum or free space. Well, in a vacuum, what's sigma? Anyway. You haven't had enough time to really hate me. I mean, just tell me what sigma is. It's what? The conductivity. What's the conductivity of a vacuum? It's an easy answer, and it's right. What is it? 0, right? It's 0. There's nothing that conducts. A vacuum is void of charge. You can't have any conduction at all. If it's 0, then I've got j omega mu. Now, if you're in free space, it's only mu naught. And over j omega epsilon. Epsilon in free space is epsilon naught. So I just have the square root of mu naught over epsilon naught. Does anybody know what that is? It is a very important number. No. No. It's the characteristic impedance is 120 pi or 377 ohms. 120 pi ohms or 377 ohms. This is very important. And what it is the ratio of E to H in free space. And this is why it's so important. If I measure an E field of 5 volts per meter, I know the H field associated with that is going to be 5 volts per meter over 120 pi. I know that ratio. That means I know what the H field is. And if I have a magnetic probe, it's called a B dot probe, if I multiply it by mu naught, then that's what the actual probe would tell me exists. It was a magnetic probe, but I'll get to that later. That's very important. It's called the intrinsic impedance of free space. Now, what you alluded to is the speed of light. Since we're on this topic of lossless, if you're in a vacuum or lossless, think about that. What was the phase velocity equal to? Omega over beta, right? You'll have to know these. So if you're in a vacuum, now I'm going to ask you another question. In a vacuum, what is the propagation constant? Gamma is equal to the square root of j omega mu. In a vacuum would be mu naught, correct? Times sigma plus j omega epsilon. What is sigma's value in a vacuum? 0, yes, that's what I'm trying to get. If you respond, you actually retain more information. Anybody here in the military? Ever been in the military? Well, if you have, you learn that verbal response helps with memory, but you should have at least. Which branch?
Air Force.
Well, didn't you have a lot of questions asked and they expected an audible response when you were being taught? No? Enlisted? Were you enlisted?
Yes.
They didn't do that? In the Navy, they did. I mean, I wasn't in the Navy. I was a consultant on board the Eisenhower. Got my hand messed up. I can't do this. But I can tell you, they taught you these are secrets of memorization, especially with pilots. When asked, repeat verbally. It'll help you. Anytime you hear something, you have a better chance of retaining it. And the more senses that are stimulated, the better the retention is. Go talk to a psychologist, they'll tell you this. An interaction I actually like, I'm trying to get with you, will make the class go faster and you'll learn more, and I'm not kidding about that. So anyway, back to this. Gamma is equal to the square root of j omega mu naught, and it's sigma plus what is the next term? Since sigma 0, it's not there. Remember? Right. J omega epsilon naught, if it's free space. Now, what do you notice happen? J omega squared square root is just j omega, right? Square root of mu naught epsilon naught is the propagation constant, correct? What's the value of alpha out here? It's not there, it is 0, right? Alpha is 0. It's no attenuation, no loss. That's my point. So in free space, there is no loss. This is simply beta. It's the coefficient of j. So that's beta with a propagation. Now, what is the velocity of free space? Omega over beta over omega square root of mu naught epsilon naught, which is really 1 over the square root of mu naught epsilon naught, and that is c, the speed of light. Since we're on this topic, what is c approximately? Anyone? A value. How fast is fast? 3 times 10 to the 8th meters per second. You know how fast that is in context? You've ever been on a jet plane? Have you ever flown? Anyone? And you can see actually the curvature of the earth when you get up further down. All right, well, the speed of light is 7 times around the earth. the actual circumference of the Earth in a second. All right? That's fast. It's 186,000 miles a second, not an hour, a second. Just think about that. 186,000 miles a second. You think to yourself, you know, in the days when they were looking for an ether, I don't know if you ever read any of this stuff, a lot of people that get sucked into engineering in the past were fascinated with physics and things like that. Well, they were looking, you know what an ether is? It's something that's necessary for wave propagation. For instance, a string that gets plucked allows the actual wave to flow, go down the string and things like this. Air is our ether for propagation of sound. There has to be something there to allow. So they were looking for this mysterious material called an ether. And they found out that there was no material. And it was faster than anything they could gauge. Then Michelson and Morley actually came up with it. But this is a very interesting point. The two laws I put up there, Michael Faraday's law of induction and Ampere's law, they are based on experimental measurements, not of things of the speed of light, but of magnetism and really electrostatics. And it really induced EMF. Those two laws give you the speed of light. Now, that's one thing about Maxwell's equations. He came up with the speed of light without actually measuring it. He induced it, inferred it from the equations, from the actual solution, which is an amazing thing about it. And even, and it's beyond the scope of this course, but do you know about the speed of light is a constant in all reference frames? Have you ever heard of that? Anybody? You've heard of general relativity, right? There's things like length contraction, time dilation. All those can be gotten at from Maxwell's equations. And there's a lot more to what I'm saying, but it's kind of an amazing thing. Anyway, that's the approximate speed of light in the vacuum, which is very important to be familiar with, because if you're electrical engineers and you go for interviews, I've been hearing stories lately about inquiries they make. And if you don't know like basic circuits, basic operational amplifiers and things like basic signals and systems, basic physics, basic this, whatever, then they kind of just move on out on most of the companies because they got a lot of applicants these days. I mean, there's a need for engineers, but I think companies are learning that it pays to filter through and find quality, because you can hire 10 engineers that don't know what they're doing, and they never will, or one good one to do it all, and that's where I think they're fixated, especially the really good companies. Google, for instance, won't hire anybody who's not like a 3.9 to 4 point, and it's got all sorts of genius accolades, and same with a lot of these high-tech companies that are super. And by the way, they pay a handsome sum too, which is nice. So it pays to know what you're talking about, not just get through school. Hold on for 1 second. Okay, I did that. Now I'm going to show you some general trickery that helps. This is stuff that's useful. And we'll do some examples. Now, any class right after lunch is always the time where I see people ready to take a nap. And I'm one of them. All right, the next thing we're going to talk about, this is how we get one H from E simply. Write this down. The H field can be gotten as 1 over the intrinsic impedance. Now that's what I just showed you before. That's this guy. Square root of J omega mu over sigma plus J omega epsilon times AP. That's a propagation vector. This is a unit vector in direction of propagation. And it's crossed into the electric field. I'm going to give you an example of this being used. Now this is a shortcut. Instead of doing the curls, curls take time, right? This is an easy way to do it. For instance, if I had an electric field given as 10 times e to the minus j 30z, or 3z, az. I mean ax, pardon. Take note of this. This is moving in x direction, or z direction. It's moving in z direction. Positive z at that, because it's a minus j times 3z. If it was a positive j there, it would be moving in the minus z direction. Do you all follow me? So that means if it's moving in the z direction, that AP, the propagation vector for this, would be AZ. It's a unit vector in the direction of propagation. Do you all follow me? Now, it's got to be a unit vector, magnitude of 1. Then it's crossed into the actual E field. Or, I'm sorry about that. This is A rho is AZ, and let's assume that eta is just 120 pi ohms. I've got the direction of propagation, I've got the E field, and I've got eta. So that means it would be 1 over 120 pi times the unit vector in the direction of propagation, which is AZ, crossed into the E field. And the E field would be 10 times e to the minus j 3z ax. That means h, notice I'm using this equation. This is a very important one. It's an easy way to get h from E for propagating electromagnetic fields. This is not for steady state E fields or H fields. Follow me? This is propagating, and I'll make a comment about that in a second. So if I look at this, what does it come down to? It's really a magnitude of 10 over 120 pi, right? Then it's times e to the minus j 3z. And what is z cross x? Y'all remember that? It's x, y, z, right? If you start at z, you're crossing x, you get y, don't you, class? So it would be in the AY direction. And that would be the H field you get. All right? Using a simple thing. Now there's a corresponding one to get the E field. Do you remember doing this with Dr. Wentworth or Dr. Riggs? You do? Okay. So when you get the E field, a simple way to get it for propagating fields is you put a minus sign down there, and then you put the intrinsic impedance here. Now it's multiplying, not dividing. And it's going to be times A rho, or a unit vector in the direction of propagation, and it's crossing into the H field. So if you're given the H field, you can get the E field, given the E field, you get the H field. Are you with me? It's very straightforward, but you have to be aware of it. And you have to do problems with that to get good at it. And that way it sticks with you. And all right, now we talk about dialectics. And I got to make one comment too before I move on this one. I want you to be attentive. You don't write anything, you just listen. You know, you've had electrostatics and magnetostatics, right? With electrostatics, no charge was in motion. Do you all remember that? Everything was pinned down. With magnetostatics, it meant the current was not time varying, it was constant. The B fields created in a magnetostatic world, or with DC currents, are there everywhere, right? But there is no E field associated with them. Do you understand that? The E fields that are created by just chunks of charge don't create a magnetic field. The reason is there is no time variation. In order for E to create H, or H to create E, there has to be an acceleration of charge. All right? Now listen up here. This is going to be important. When you learned about capacitors, you had two plates on a capacitor, right? You put a voltage difference that was time invariant, and it created electrostatic energy, mainly between the two plates, right? It also created stray fields around there, correct, class? But all the energy, and once you charge a capacitor and you discharge it, you can get all the energy that you put into it back. You follow me? It's conservation of energy. If I charge up a capacitor to 5 joules, I can burn 5 joules in a resistor if I discharge it. Now with an inductor, you have magnetostatic energy, and the energy in an inductor is 1/2 Li squared, isn't it? Now that energy, it's from a static magnetic field around that inductor, and when you short that inductor with that current into a resistor, all that energy is deposited back in there. With me? Now, if you have what's called an antenna and it launches electromagnetic energy, where we have an acceleration of charge, it creates E and H fields that are never to return. They're uncoupled from the device that created it. That's a launched wave. It's just like a sound wave or an ocean wave. It's never coming back to the one thing that created it. And that's the thing we're talking about here when we talk about propagating electromagnetic waves. These are things created by the acceleration of charge, and they're not related to static DC fields, either magnetostatic or electrostatic. This is important to understand. So these are uncoupled from that. It's very important. And we'll talk more about that later. Keep that in mind. Now, when we talk about dielectrics, I've got to tell you one thing. Dielectrics, the only perfect dielectric is a vacuum, theoretically. But with dielectrics, as good as they are at preventing charge from moving through there, there's still some leakage current. Here, if you think about dielectrics for a second, think about just very low conductivity materials. Right here, do you know having a flavor for conductivity, for instance? Like if I have two plates here, just say 1 meter square plates, and I'm separating by a meter. Well, if there's liquid metal between them, the resistance is about 0. Are you with me? Now, the conductivity of metal is about 5 times 10 to the 7th or so. 10 to the 7th of the order. Ohms, 1 over ohm meters. So, make a long story short, resistance is proportional to 1 over conductivity. So 1 over 10 to the 7th is 10 to the minus 7th ohms of the order of that. Just hang on for a second. Compare that to the atmosphere. Right here, we've got a conductivity about 10 to the minus 14th. All right, 1 over 10 to the minus 14th is 10 to the 14th. It means over that same area, we have about 10 to the 14th ohms, or we have an immense amount of resistance, right? But we still have enough, there's still resistance will let a little current leak through there. Do you follow me? The way they quantify that little bit of current leaking, they don't use conductivity. They use something called a complex permittivity. And they say they call epsilon complex as epsilon prime minus j epsilon double prime. Now, don't get messed up with this one. So, now we take a look at curl of H again. That's Ampere's law, and I want you to do something. Call that now, this is not in the book, Jm, and this is Maxwell current density. My old professor, when I was doing a PhD named Les Tell, he used to refer to that as the Maxwell current density. And we wrote a paper about it, and it was published in Nature magazine. It was my first journal article. Now, Maxwell current density is a summation of both the conduction current, so it's sigma E, plus the displacement current, which is plus j omega times now epsilon complex, which is epsilon prime minus j epsilon double prime times E. Just work with me here. You all see what I've done there? I've replaced epsilon with epsilon complex. What that does is this. What is j times j, anyone? It's minus 1, isn't it? I mean, j is the square root of minus 1. J times j is minus 1. Minus 1 times a minus sign would be plus, right? So this could be rendered as sigma plus omega epsilon double prime times E plus j omega epsilon prime times E. Now, you'll notice that this is now related to loss. And it's not just conductivity anymore, but it's omega epsilon double prime. And I have to say one more thing about this to try to drive this point home. When you see sigma being used, conductivity, think of metal. With metal, or think of something that's a decent conductor. So if you could, theoretically in your mind, paint a dot, make some electron red and watch it, it would literally go from one end of that rod to the other. Do you follow me on this? It would flow all the way through. When you have this term epsilon double prime, nothing flows all the way through. What happens is they're like locked in dipoles where they have a plus and a minus. And as you get a time varying field, they're wobbling. But when they wobble back and forth, they actually frictionally heat the lattice. So there's a loss, there's ohmic losses in the actual material. You follow me on that? That is related to the epsilon double prime. It's a polarization current. It's literally having things just wobble back and forth and heat up the lattice because they're doing that. That's what's going on. So this is really a complex permittivity. And if you assume sigma is 0, you don't even have to assume sigma is 0. The way they usually talk about this, when they talk about curl of H, they do this. They're going to show you something on the real axis. And that real axis value will be sigma plus plus omega epsilon double prime times E. And on the vertical axis, this will be called the imaginary axis, or the J axis. They're going to have something, this will go out to here. And this will be equal to omega epsilon prime E, or it's this term. Now, when you look at this, you get this. This is Jm. That's the total of this and that together. You with me? But this angle is what's important. There's a symbol they use there, and it's a delta, and this represents the angle between really the real current here and the loss current. But think about this. This is the real current here on that side, right? So opposite over adjacent is tangent. So the tangent, the tan of that angle is equal to sigma plus omega epsilon double prime over omega times epsilon prime. And this is called the loss tangent. Now here's why this is important. We'd like a loss tangent of 0. We would like no loss at all if we have a dielectric and we want it to behave as a dielectric. What we'd like is this. We'd like that angle to be 0, but it's not. So the loss tangent itself is an indication of how good of a dielectric it is. When you get loss tangents down there at point, and it's a function of frequency of 0.0005, like 5 times 10 to the minus third, 5 times 10 to the minus fourth, that's good material. That's low loss at that frequency. You get materials with a loss tangent like 0.1, 0.2, you got a problem. You're losing a lot of power. You're losing a lot of signal. Just remember that as a gauge. And this course goes till 2:30, right? Is that right? All right, well, technically I'm done. I didn't get to my conductors yet, but I will next time. And I'll start there. Do me a favor if you can. Bring your books to class. I do this all the time when I was a student like you. I write in my book. I mean, I'll sell back organic gardening or philosophy of Plato or something when I was in your shoes. But I'll be darned if I'm going to part with any of my textbooks that I learned from, because that's usually your bread and butter go-to. My old, did y'all have, who did you have for physics? Do you have Kepler, Halliday, or Resnick? What physics book did you use? You don't remember? What your calculus books you had, right? I mean, those are like Bibles. I mean, because I mark those, especially when you're a senior. You have books there that you inked up because you knew that someday you're going to go back to that and grab that, especially with physics, the things that don't change. Physical laws don't change, neither do mathematics. Now, admittedly, the data book I had back in 1985 and 86 is something I've thrown out long ago because there's always generations of new components. But physics, mathematics, and fundamental engineering, electromagnetics, and things like that doesn't change. This is stuff you want to stay with, you want to keep. All right, guys, you're a lively bunch.